Okay, so we just observed water flowing out of a get into the picture here. Nice uniform cylinder with a little spout at the bottom. And as expected, filled it up, released it. There was a water stream. It fell approximately 1.22 centimeters, meters, sorry, 122 centimeters. You might want to write that down. Fell 122 centimeters. Fall 122 centimeters takes about, I'm thinking 0.44, 0.45 seconds. You can work that out very easily. We timed it, got black marks there approximately every 5 centimeters. So we timed the depth versus time. I actually timed the time intervals, but it was a lap timer. So if we add up the time intervals, we get the clock times. Okay. And then we had a meter stick lying on the ground. When I initially released this, when it hit the first mark, the thing was at about 70 centimeters. Okay, the stream was landing about 70 centimeters horizontally from where it started. The tube is pretty much horizontal, might have a very slight downward slope, maybe 0.02, 0.03 radians. Just looking at it, you can make your own judgment. This thing was sitting on a horizontal surface. And you can see that the initial velocity wasn't perfectly horizontal. Okay. So that could make a difference in some of our analysis because we do want to analyze that projectile. But what it comes down to is, people told me, well, what's going to, I asked what's going to happen when I release this? Well, I said there's going to be a watershed. Well, a lot further than people expected. Twice as far, even maybe a little more. It's kind of surprising. And you'll see why that happens. Water's going to descend here. We can time it. Nobody really said it, but the water's going to descend more and more slowly. Okay. Now that is totally connected, closely connected to the fact that the stream doesn't go as far. Stream doesn't go as far, it's because water's not coming out as fast, which means you're not losing as much water for the time. The rate at which you're losing water decreases. So that the rate at which the water depth changes is going to decrease since you have a uniform cross section. Okay, well, we can calculate all that, and you will. Part of your homework. But here's the data though. Okay, little picture. We have the tube and the spout, and you got water here. And just to show that it's water, we put a little sharks in it because our sharks in all water, I think. Okay, the ones we drink are really small. Okay, well, when this is sitting on a brick pillar, water comes out, hits the ground. This distance here is X. The distance here between the spout and the water level is Y. So that's the meaning of Y, that's the meaning of X. And now we got running times for the depth versus time. I did comment the first time I ran this experiment back in the days of DOS, I got incredibly accurate results. After predicting, using the differential equation we'll solve here in a couple of minutes, after predicting that this ought to be the depth ought to be a quadratic function of time, and nailed it to the pixel. And even in the mid-90s, 2 pixels were pretty small. So that's pretty neat. I thought that was one of the neatest things I've seen in analyzing data. One of the big surprises I ever got. Okay. Here we did lap times, which is fine. And I added up the lap times in my head. Okay. So we don't take these things too awful seriously. But I kind of think they're okay. I got a total running time of 49.82 seconds. And the running time here was 50.11 seconds. That's within about 0.3 of a second. Meaning I could have made an error in this decimal place. And been off by 3 in this decimal place, but these are pretty good times. Okay, they should be pretty good. Okay, well, let's see what we've got. Now, as I said, I like to do things by hand before I do it by machine. It's really easy to sketch a hand sketch graph with reasonable accuracy. See what the graph of this looks like, and then what a graph of this looks like. Okay. So I'm going to just do that right here before your very eyes. Going to do Y versus T, and I'll put 60 out here. T is in seconds. So I'll simplify that. I get 30 in here. I'm trying to do this fairly carefully. Here I've got 10, 20, and 40, and 50. Now, some of those 10-second intervals are a little long. That one looks a little long. Some of the others look a little short, so we're not going to get a perfect result. But I just want to see what it looks like. I don't want to have to go to a computer and enter everything in. Okay. Okay, now I've got my depths. So I'm going to make this as accurate as possible. I'm going to go all the way up to 32 for my depth, because then I can divide each interval. 32 divided in half gives me 16. Divide that in half. There's 8. Divide that in half. There's 24. And then I can divide those in half. And keep in mind what the numbers are. At 0 seconds, I get 25.1 centimeters. At 25.1 centimeters, being just a little over 24 centimeters, I'm going to put a point here. 20.2 centimeters at 6.09 seconds. Now, 6 seconds, there's half of 10. 6 would be about here. 20 would be here. So I come over this way, and then I come up to the 6 second mark, and I get a point here. I'm not being overly, I'm not taking a ruler and stuff. I'm going to do this in Excel, or you're going to do it in Excel. And you'll see just how close it comes, and you'll get even more information that you can't just do quickly in your head. Okay. You get a trend line. You get information on how good the fit is. But you kind of do that by eyeball too. Okay, so anyhow, 13.15 seconds. Well, that's going to be 13 about here. And we're down to about 15 centimeters, which will be about there. And then 20.41 seconds, that's going to be about here. And we're going to be down to about 10 centimeters. And there's 12. 10 is going to be about. Yeah, so my points aren't great. Okay, 31 seconds. Now, so we're going all the way up to 31 seconds here. So it's going to be like this. And 5.3 centimeters. Well, 5 centimeters is going to be a little over 4. That's going to be here. And then 50 seconds by the time we hit 0 centimeters. So we have a point here. And well, if I do nice smooth curve, following this trend line, it's very plausible that I've got a quadratic function with its vertex here. Okay. Now that's just a plausibility. At this point, I was a little low with estimating that point. I didn't do a very good job, but I actually kind of hit all the others. Okay. And I did an honest approximation. So that tells me, okay, I know my curve has this shape, so when I do it in Excel, and Excel shows me a corkscrew shape, I know I gotta fix my Excel, okay? Now, it's not gonna be Excel's fault, it's gonna be yours if you get a bad shape, but at least you know what it all looks like, okay? Then I do my X versus T. There's my 60, put 30 there. And I know what those numbers are. So we got to go up to 70 centimeters, which is convenient. If I take 80 here, then I just got to divide this interval in half. It's 40 about here. Divide that in half. It's 20 about here. There's 10 and there's 30. Divide this in half. That's 60. There's 70. There's 50. Okay. Now I just got my points. 9.89 seconds is going to be pretty close to 10 seconds. That's going to be 70 centimeters. Down here, and up here, I got a point about there. And 60 centimeters is going to occur at 15.69 seconds. Well, that's going to be. Remember, when I wrote these down, I didn't write 0 here. Each of these should be 1 unit lower. So 70 centimeters is actually at 0. 60 centimeters will be at the 9.89 seconds. Okay. And it wasn't making sense. Okay. And you kind of got to be alert to the fact that what you're doing is probably not always going to make sense. Okay. Then 50 centimeters, 22.63. Forty centimeters, 30.50. No, my 50 is way too close to my 40. So there's got to be a little fuzziness to my graph, but it'll smooth out. Okay, I think. And 30 at 36.70. Would be about here. 20 at 41.50. 10 at 46.50. And 0 at 46.50. 0 at 49.82. Okay, well, that's not really all that beautiful because of the anomalies of hand sketching. But if I take the meter stick here, which is probably dry now. I can put a pretty doggone good straight line to that data, okay? Okay, well, that's data now. What's the physics of this thing? And we talked earlier about point forces and stuff like that. And after talking about this and so forth, people said, well, this is going to decrease. This main horizontal range is going to decrease due to the decrease in the amount of water above the hole, which is pushing down on it. Well, that's really pressure. Okay. The water, but you know, that was a really good way of stating it. So picture here. Get the shot straight. Okay. So the water up here is being supported by the water right here, isn't it? I mean, what's holding that water up? Water below. Okay. So we can say at this point, we're supporting all this water, which is putting pressure. That water is putting pressure on this well. Okay. Pressure has the convenient or inconvenient characteristic. Okay, fill up a Ziploc bag with water and see, poke a bunch of holes in it and squeeze it. At every point, that you can actually do, get a Ziploc bag, it doesn't cost much, you're gonna ruin it, but put little pinholes in it. Okay, so little pinholes and squeeze it so the water comes out. Probably will, even if you don't squeeze it. If you squeeze it, you can feel you're adding pressure, having defined pressure. That comes along. Okay. And if there's a hole here, it's going to shoot out this way. If there's a hole down here, it's going to shoot out straight down. If there's a hole in the side, it's going to shoot out the side. Okay. In the case of this cylinder, the pressure causes water to shoot out this way. You conclude pressure acts in all directions. And it acts equally in all directions. Now we can get that theoretically with will. Okay, so the pressure causes the water to come out. Pressure exerts a force on the water. So the water just on this side of the tube is feeling the force of the pressure. The water on this side is only feeling atmospheric pressure. Atmosphere is already pushing down on the top here. So the actual pressure here exceeds atmospheric pressure by the pressure you get from this much water. Okay. So that causes the water to flow out. Another way of looking at what happens without having to go to pressure and everything. And of course, we want to go there. When you lose water down here, or when water comes out here, you lose water up here. So the system has potential energy change. Okay. So in terms of the potential energy change, potential energy changes results in kinetic energy as water coming out here. Okay, as water descends, the PE changes. Ideally, is equal and opposite. Delta P is equal and opposite to delta K. Okay, or delta U and delta K. Okay, and abbreviated you want to. Notation. Okay, so no, I'm not connecting it. I'll talk about it more loud. It follows that dy dt is negative K square root of Y. Your change in potential energy is going to be proportional to the square root of the velocity you get. Because your change of potential energy is proportional to Y, and your change of kinetic energy is proportional to V squared. And dy dt is how fast water descends here, which is directly proportional to how fast it comes out down here. So you get this differential equation. Now we'll flesh that out a little bit. I'll send you some questions in email and ask you to answer before that. Okay. Because we're running real short on time. How do you solve this equation? Well, I'll solve it for you. Separable. Okay. And that's the y over the square root of y. So if we give them a t, so I wrote it. Okay. Well, you integrate dy over the square root of y, you get square root of y. But you get 2 square root of y. Okay. And this is going to equal negative kt plus an integration constant. So that Square root of y is this, so when you square it, you get a quadratic. That's why this thing ought to be quadratic. Now we'll worry, we don't have time to worry about those things and so forth. But that's just your initial condition, that y of 0 equals 70 centimeters. Okay. You can make that adjustment. Okay, so that's just standard differential equations. Y'all just finished the differential equations. Suppose everybody did okay. Okay, so I assume that you could have done that yourself. Okay. Well, there's some really kind of neat subtle connections here that I'd like to have time to do today, but see in 2 days. And I'll email you some questions. Lead you to there, so we can see a little bit more about what's going on with this whole system. Okay. And we can derive Bernoulli's equation and stuff.